So Sage 9 was released on New Year's Day 2020, and we got some nice new function field code in the new release, and I'm just going to do a quick overview of some of the stuff you can do now with function fields in Sage 9. So first of all, just a couple definitions. A plane algebraic curve is a curve defined by a polynomial equation in two variables. This is what we're going to be working with the whole time. So here's some just basic examples. X squared plus y squared equals 1, the circle, the unit circle. Here's y is plus or minus the square root of x to the fourth plus 1. So we got these kind of flattened parabolas here. This is an interesting one, y squared equals x cubed plus x squared, because it's got a point of self-crossing here, a singularity. And you're not limited to squares of y. It can be arbitrary powers. You can have mixed powers, x times y. It's just arbitrary polynomials in two variables. An algebraic function on a plane algebraic curve is a rational function in the two variables. So 1 over x, x times y, just basically any polynomial divided by any other polynomial. What is the utility of an algebraic function? Well, they're useful, among other things, for integration. An abelian integral is an integral of an algebraic function. So, for example, this integral, 1 over x times the square root of x to the fourth plus 1, this is an abelian integral. Why? Because we can express it in this form. We can say, y is basically this square root, so y squared is x to the fourth plus 1, a polynomial relationship. And then the integrand takes the form of 1 over x times y dx. So we're integrating an algebraic function, a rational function of x and y, on an algebraic curve, and that is, by definition, an abelian integral. Sometimes you look at these rational functions, 1 over x times y, you might think to ask, well, what happens if, this relationship doesn't hold? What if, I don't know, they're both 0 or 1 or something other than y squared being x to the fourth plus 1. Well, it's like asking, what happens in this equation if this quantity here is not the square root of x to the fourth plus 1? And the answer is really just doesn't matter. It is the square root of x to the fourth plus 1, and we're not interested in any other cases. And that's the answer here. We're only interested in 1 over x times y, subject to this constraint, y squared equals x to the fourth plus 1. So, if we have an algebraic function on an algebraic plane curve, what can we do? Well, we got some basic questions that we would like to answer. First of all, where are its poles and zeros? Just like with a rational function of one variable x, where we factor its numerator and its denominator. Where is it 0? Where does it run off to infinity? Can we do a series expansion in any particular point or place? Point is point. Just the usual term. Place is a bit of technical terminology here on a singularity. This point of self-intersection here, this is a place. That's what it's called. It's two places. Everywhere else in the curve, you got 1 point, 1 place. But here, we have 1 point and 2 places. We have 1 place for each of the branches of the curve where it crosses itself. That would be 1 place corresponding to this branch, and 1 place corresponding to that one. So, and the series expansions are different on the two branches of the curve. So when you're dealing with singularities, we do start to distinguishing points and places. But really, one of the nice things about algebraic curves is, you think if we were to just do, any old function of x and y equals 0, well, this could be just about anything. By restricting it to a polynomial, it's a very well-known case, and in particular, once you figure how to deal with singularities, that's it. That's the worst it gets. If you can deal with your singularities, these points of self-intersection, then you can handle an algebraic curve. You can a rational function, algebraic function on an algebraic curve. The singularity is the worst it gets. So we want to do series expansions at any point, and for singularities we might have multiple series expansions at a given point. There'll be expansions for each place. And then finally, given a set of poles and zeros, can we find, if we know go the other way from 1, if we know what the poles and zeros are, can we find a matching algebraic function that has that set of poles and zeros? And with the new code in Sage 9, yeah, we can do all these calculations. So here's Sage 9 up and running. These are just the plot commands I use to generate, these drawings here. This can be these graphs of algebraic curves can be made using the implicit plot command. That's not new in Sage 9. What's new are is the function field code. In particular, we could do this before over finite fields, but now we can do it over it's Q, the rational numbers, or I think is often a very useful choice is QQ bar. It's the algebraic field, so it's not only just the rationals, but all roots of polynomials, and that is often very useful for a lot of time. You can plug in just a rational number here, and you see that you're going to get something. If x is, of course, in the circle, x is 1/2. Y is going to be the square root of 3/2. So right off the bat, if you put in a rational number, you might get algebraic numbers on your other variables. So it's often very useful to use QQ bar. It's algebraically closed. That's the nice thing about it. So we don't we can't yet set this up using just a regular old polynomial ring using standard Sage syntax. It's function field syntax is just different. It really is it's a rational field in X. It's just ratios of polynomials. That's what this is. Just a different syntax that gives you a different set of features. So what do we want to do here? I'm going to go to I'm going to create a polynomial ring over that with a capital Y, and then I'm going to restrict it to construct a polynomial that then restricts it to one of the cases, to my my function field, my algebraic curve. So I'm going to do R extension, and now I'm going to say, let's just do the circle. Let's just say y squared minus x squared, y squared plus x squared minus 1. So that's going to be now just the circle. It's a function field in y, and I just y, and the capital Y would be the full polynomial ring, and now L is, this y is, that y modded out by this polynomial. So we're now in a function field on the circle. And what can we do here? We can, let's see here. We can, let's see, one of my questions. I can, actually let me switch to the little more interesting example, I think. We'll do this one. We'll switch to this. This is the, right, y squared is the square root of x to the 4th plus 1, the second one here. Okay, so let's say here we want to do we want to do the poles and zeros of this one, because this is the integral example. So I'm going to do the poles and zeros of 1 over xy. So I can construct 1 over x times y, and it actually normalizes it by moving the y into the numerator, and then I can just say divisor. And this is going to give me a list of all the poles and zeros for this function on this curve. You'll see I've got some long decimal expansions here. Calculations in QQ bar are exact. I set my display format to be radical and do this calculation. You'll now see these things displayed in 4th root of -1, which is, yeah, I guess what this is here, square root of 2 minus square root of 2I. Yeah, this is going to be a fourth root of negative 1. Yeah. So, what do we got here? We've got some places at infinity. 1 over x. We see the 1 over x there. We know that this is a place at infinity. 2 places at infinity, each with third order zeros. That's why they're positive. And then poles at a bunch of other places. X is, actually it's better up here. Minus square root of 2 minus square root of 2I. Minus plus, plus minus, plus minus. A bunch of zeros there, and then all first order. That's why there's no 3 star or 2 star in front of them. And then zeros at x0 and y1 and x0 and y negative 1. So it tells us where all of our zeros are, our poles and our zeros. So now we want to say, let's say we want to do a series expansion around, well, first of all, we can just say, let's just do a series expansion around one of these. Let's, what am I going to do here? I'm going to say support, I don't know, let's just run 4 it is. Okay, so there's one of them, so a PL for place. This is the place at x0, y1. So what is that? Where is that here? x0, y, yeah, it's this point right here on the curve. And I'm going to say L completion PL, and I'm going to ask for the function 1 over x times y, and it's going to think for a minute, and it's going to give me a series expansion of, and that is that's a pole. So I'm going to expect not only a series expansion, but a series expansion that starts with like a negative 1 power. Perhaps a default precision is 20 terms, and we do have all this operations in QQ bar, the algebraic field. They can be slow. This one is running a little slow. Let's try it at a lower precision. Let's try precision 5. There we go. Maybe a little more than that. 8. Okay. So we have a 1 over s minus 1/2 s cubed and higher order terms. So we do a series expansion. It's kind of indeterminate here just what the expansion variable is. That's probably going to be a feature we'll add in Sage 9.1, is to actually set the uniformizing variable, as we say. But let's just say we wanted to expand in x. We just wanted to do this expansion in x. So how can we do this? Well, we can just do x expansion. We'll do this. It seems like an awfully roundabout way, but so we do x expansion. It looks like s is the x expansion. So then what I could do is I could reverse this. It says s, but it's actually, by reversing it, it's giving me x. It's giving me s expanded in x, and I could then substitute that back in to this here. And it's not going to change anything because it sure looks like that x is the uniformizing variable. Yeah, I think it is exact. This is again another feature in Sage 9.1 that when it's exact, it'll drop this order, this higher order term order. But right now, all it indicates is that it's exact up to 15th order, and s is x up to 15th order. It probably is x. But anyway, if it wasn't x, you could do this trick where you do x, expand x, and then substitute back into your completion, and then get this series expansion in terms of almost any variable you want it to be. We probably couldn't do y. It looks like there's because the slope is 0 here. It looks like we couldn't do y is not going to be a suitable expansion variable there. We can take a quick look at that and see. In fact, it is not. I don't think it is. Let's see. Yeah, this would have to be an s here. It has to be an s. Well, maybe y minus 1. But even that is not going to help us any, because we're still going to have a 1/2 s to the 4th We need a fourth root of y to do an expansion, doing anything, fourth root of y minus 1 to do any kind of y expansion here. But you can see that it can do these expansions. What else is on our list? Okay, find the poles and zeros, construct a series expansion, and then given a set of poles and zeros, can we find the matching algebraic function? So, going back to, where's our divisor? Call it D for divisor. There's our divisor, and now I can, this is standard function field terminology. We actually want to invert divisor, which is just negative D. It just switches all the poles and the zeros. And that's what we want to ask for basis function. Is that right? Basis function space? Yeah. And well, that is actually the, that's 1 over x times y, just normalized to put the y in the numerator. If we wanted to do something, I mean that's just it. I mean, you know, we just basically gave it these sets of poles and zeros and told us find a function that matches if one exists, and there it is. It just found us one. A little more complicated example. Let's say we wanted a function that matched at all of the poles, but not necessarily the zeros. We just left the zeros alone. And how could we do that? We could say divisor of poles. You see, now we just got the polar part. The signs all changed, but we got the polar part there without the zeros here, and then we could say 0 basis function space again. It uses the Hess algorithm, and there is our original the function we were looking for there, which is part of it's a vector space, because by taking the restriction off from the zeros, we gave some more freedom into the system. So yeah, those are some of the basic calculations you can do with the new, I should say one more thing, and that is a resolution of a singularity. Let's just jump over to, let's change this to the other, what is this, x cubed plus x squared. Yeah. Okay, and well, let's see here. What do we want to do? Let's notice that at this point, let's say the function, let's look at y over x. I mean, it looks like the slope here is 1. This is slope, basically y over x. Okay, this one is 1, and this one here is -1. So we expect that expanding this function out is going to give us 2 different series expansions, and they're going to be that you can see this thing is symmetric around the x-axis. They're just going to be negatives of each other, but one's going to start with 1, and the other one's going to start with -1. And let's see how we do that. I want to do a decomposition. Do a maximal. I have. I'm working in projective space, but I can pick either my affine space, which excludes the line at infinity, or I can work at infinity. Right now I want to work in my affine space, ignoring infinity, simply because this point is at the origin 0, 0. It's not in infinity. So I'm just going to say maximal order. I'm going to ask for a decomposition. And what do I want to decompose? I want to decompose something from R as maximal. R is the, it's going to right. Well, actually not really. But R is just the rational function field in X. So, what did it just decompose? It decomposed, it looks like it just decomposed the point at the origin, actually. This is what I expect. I expect to have to ask for an ideal, and I'll give it the x coordinate at the origin, and I get the same answer actually. But what I get is a decomposition. If I were to do this at, say, x equals 1, I'd get the 2 points here at x is 1. It looks like it's y is going to be plus the square root of 2 or minus the square root of 2. Makes sense, right? I guess if you them out, it probably works. But here at the origin, they split apart like this, even though you have 1 over x here. X is 0. So you would think this would be infinite, but actually in the limit, it's not just 1 over x, but y over x. And the limit is approach 0, y over x is finite along these two branches of the curve, even though x itself is infinite. So given my decomposition here, let's take 0. So this one here is going to be an ideal. I'm going to convert it to a place. Very close relationship. Prime ideals correspond basically to places. But, you know, if the ideal wasn't prime, it would complain when I tried to convert it to a place. I'm going to do an L decomposition. No, I'm going to do an L completion. It's a series expansion at that place. I'll just ask for my precision to be like 5 terms, so we can get this done today. And ask for y over x to be expanded. And there is, I expected an expansion starting with 1, and there it is. Well, why is that? Because if this y over x is 1 in the limit at this place, what about the other place at x equals 0? That's this one. That's the one where y over x is negative 1. Do the expansion here, and now we get the other series, the negative 1. Series corresponding to this curve there, this curve here. The first one gave us expansion along this curve here. So obviously you have to learn something about algebraic curves. You may already know a great deal about algebraic curves. I hope so. If not, you'll have to take a look at a book on algebraic geometry. Maybe even my book, if I ever finish it someday. But right now, these are some of the nice new features that we have in Sage 9 to do calculations on algebraic curves.